So again, all these rules are typed up on that handout. You don't have to worry about typing them. They're all on that worksheet that you have. The only one I think that's not on there that maybe you need to take into account is that anything raised to the 0 power is always 1. Anything raised to the 0 power is 1. So I don't think that's on your handout, but that is somewhat useful to us. So the other two rules have to deal with log and natural log, and then evaluating them at particular points. So log base 3 of 81 is equal to essentially a y. And then if we apply our rule, the rule is a to the y equals x. So a is our base. So it's 3 to the y equals 81. So when I'm trying to solve for that, the y value we're looking for is what? 3 to what power is 81?
3.
4. 3 is 0.7. So the answer is 4. Log base 3 of 81 is equal to y, but y is equal to 4. So 25 equaling 5, well, that's kind of like saying, okay, 25 to what power is 5? Not 2, 25. Yeah, 1/2. We need it to be a square root. So log base 25 of 5 is 1/2. Log base 10 has to equal 0.001. So again, the question becomes 10 to what power is 0.001. So 0.001 is really the same as what as a fraction? Okay, let's go to this. 0.1 is what is a fraction? So 0.01 would be, so 0.001 exactly, it's 1 over 1,000. So it's like saying 10y equals 1 over 1,000. So 10 to what power would get you 1,000? All right, 10 to what power gets you 10? 10 squared gets you 100. So 10 cubed would get you 1,000. But this 1,000's in my denominator, so it'll be negative cubed. So you have equals negative 3. What do we know about the natural log of e? They kind of just cancel each other, right? You know a lot. The natural log of e is really just their power, so in this case, negative 100. The natural log of e is kind of like saying 1/2 times 2/3. So 2's cancel each other out, and you're left with 1/3. Okay? We can also use logs to evaluate problems that are set up to be longer or shorter. So in the case of this problem, it says evaluate, so we're still doing the same thing. But what we can do is, since these have like bases, we can actually turn this into one problem. So if you look at your properties of logs, log base a of x plus log base a of y is really the same as log base a of x times y. So it's really the same as log base 4 of 64. So then the question becomes, okay, 4 to what power is 64? So our answer is simply 3. The whole thing or just the answer?
Like the whole 7 equal.
Log base 4 of 2 plus log base 4 of 32 is our rule number 1 here that says 2 logs with the same bases being added are really multiplication of their inside. So we multiply the 2 and 32 to get 64, and then a base is 4, so you have to figure out the power that would make it 64, which in this case is 3. Subtraction is the opposite property. It turns to division. So you get log base 2 of 80 divided by 5. So 5 goes into 80 16 times. And then the question becomes, okay, 2 to what power is 16? 4. So this is kind of like what we call contraction. We took a long logarithm and we shrunk it into a singular logarithm. We can do the opposite of that, which is to expand a logarithm. So right now we have the natural log of all of that. And what I want to do is get rid of the exponents, get rid of the division, and expand it out. So the first thing I do when I see a problem like this is get rid of the division. So the natural log of all of that is really the same as the natural log of 3x squared minus the natural log of x plus 1 to the 5th. So you see how that's literally just the opposite of what we just did. Now, what's nice about natural logs is their powers can be brought out in front. Now, where you have to be careful is this is 3 times x squared, but the 3 isn't being squared, only the x's. What do we know about two things being multiplied together? It can turn into addition. So this needs to become the natural log of 3 plus the natural log of x squared minus the natural log of x plus 1 to the 5th. Now I can bring out my exponents as numbers in front of the natural logs. So I get ln 3 plus 2 ln x minus 5 ln of x plus 1. I have no idea why it flipped. Just like a random question. That is expanded form. Now, addition does not separate. Addition does not separate. Do not try to make that like the ln of x plus the ln of 1. That's not possible. That same rule can be applied forward to backwards. So on the last rule, we turned all the multiplication and division to addition and subtraction, and then we did the exponents. When we go backwards, they like to bring the exponents in first and then turn it back to multiplication. So this will be ln 3 plus ln 8 to the 1/3 power. Well, what do we know about 8 to the 1/3 power? Yeah, it's simply 2. Because the cube root of 8 is 2. So this becomes ln 3 plus ln 2. but the plus can turn to multiplication, so you get ln of 6. The same thing is true for variables. So again, this is like a numerical example. Here's the variable. ln x plus ln y to the a minus ln z to the b. Turn addition to multiplication. So you get ln x y to the a minus ln z to the b. And then turn subtraction to division. So we get a final answer of ln x, y, a all over zb.
Could you just look at that, instead of trying to combine the pluses, just do the pluses on top minus negatives on the bottom?
Yes. Okay, and the last review part is simply being able to solve for these variables. So can you get an answer numerically for an x value, which means can we isolate? So if you have ln of x equals 5, goes back to how do I get rid of ln? E both sides. So you get x equals e to the 5th. That is considered solved. Because e is a number. So it's a number to a power. Okay, once again, ln has to be isolated to do this. So we got ln on one side, numbers on the other. We can e both sides. E's and ln's cancel. So you get 5 minus 2x equals e to the negative 3. Isolating our x, we're going to subtract 5 from both sides. Then divide by negative 2. I would personally break it into 2 fractions so that I can get rid of my negative exponent. So I have negative 1 over 2 e cubed plus 5 halves. So I'd split the 2 under each and drop the e down. Okay, example 3 is a little trickier. You cannot e both sides because I have ln's on both sides.
Can you bring an ln over the other side and then do multiplication?
That's exactly what we have to do. You have to add the ln to this side. So that you get ln of 2x plus 1 plus the ln of x equaling 2. And then we need to use our expanding and contracting property to say that addition of 2 natural logs becomes multiplication, so that you get the ln of 2x plus 1 times x, all inside my ln, equaling 2. So then, if you e both sides, I would distribute my x to the 2x and the 1. So I'd have 2x squared plus x equals e squared. And then it's a quadratic. So like when you move it over, it ends up being the quadratic formula. So you can just kind of like factor it. So because since you have e squared, it'll be e and e. Yes. To be honest, I'd probably just throw it into quadratic formula because factoring it with an e is going to be trickier for you to see. So it'd be -1 plus or minus the square root of 1 minus 4ac all over 2a. Now I knew since c was negative and that's negative, I just turned it to positive. Again, that is a numerical answer, so you don't have to take it down any further. It's like 1.6883. Okay. So now these are the reverse of that. Now we have e's and we have to get rid of e. So to get rid of e, the rule is still the same. We ln it. So we're going to ln both sides. So we get 5 minus 3x equals the natural log of 10. Much like e raised to a power, the natural log of 10 is simply a number. Subtract 5, divide by -3, and you get x equals -1/3 ln 10 plus 5/3. You could have left it as one big fraction, two small fractions, doesn't matter, same property. Bringing the 1/3 in on the 10 doesn't help because 10 is not a perfect cube, so we don't have to like bring it in. But if it was like the number 8, I might have brought it in just to like help me see it better. Okay. Once again, same idea. You cannot take the ln until the e is isolated. So we have to add over that 7. Then we can ln both sides. So you get 2x plus 3 equals the natural log of 7. So x equals the natural log of 7 minus 3 all over 2. Okay, and last but not least, so this idea here is actually going to be an algebraic process as well. So we have 7e to the x minus e squared, in a way, to the x equals 12. So what we're going to do is bring everything over to one side and get this set equal to 0.
Why do we either just subtract 12?
No, then you have a negative e to the 2x. Move it to that side. It's more positive. So you get e to the 2x minus 7e to the x plus 12. And then what I want you to do is treat e to the x like the letter u. So everywhere I have e to the x, I'm going to make it the letter u. So here, since there's 2 of them, becomes u squared. So it's kind of like e to the x to a power of 2. So now you have u squared minus 7u plus 12. So are there factors of 12 that have a difference of 7? Yes. U minus 3, u minus 4. And then if you have a quadratic and you factor it and you're solving, what do? You say, okay, u equals, and u equals 4. Like that's how we solved quadratics back in the day, through factoring. But now our u is really, so this is like saying e to the x equals 3 and e to the x equals 4. But I want to know what's x equal. So if you ln both sides, x is equal to the natural log of 3 and x is equal to the natural log of 4.
It's a quadratic.
Yeah, so like when we turn it into the quadratic here, that shows that this is raised to a power of 2, and it's giving you that quadratic feel. So again, in order to really be able to take derivatives of e's and ln's, the properties of expanding, contracting, and manipulating is super important. So in your textbook, they actually have the quick review is all about these types of problems. So what we're going to do is the 3.9 quick review as well as 1, 3, and 5. So it's all of the quick review as well as 1, 3, and 5. From page 170. So I'm not sure the quick review and 1, 3, and 5 are on the same page. I think they're not.